My name is Francesco Longo. I'm going to chair this session today. The title of the session is Additive Manufacturing, Technological Advances, Challenges and Impacts. We do have 4 speakers today in this session. We will start with the first speaker, Joseph Canou, that is going to present a low-cost subtractive method for finishing 3D printed structures. Joseph, the stage is yours.
Yes, thank you. So first, good morning to all of you. Maybe I will turn off my camera to avoid having some problem with the transfer. And now I will share my screen. Well, at least the document. Something like this. Okay. Do you see my screen?
Yes, perfectly.
Yes? Okay, thank you. So I'm going to present this paper, a project we worked on to develop a subtractive method for 3D printing using concrete. So maybe the first things to say is that these developments were made in the frame of a European project called HINDCON, Hybrid Industrial Construction. The idea was to build a 3D printing all-in-one machine, so it means able to print, but also able to do some subtractive action, some machining for large-scale manufacturing process. So it was a big European project with 12 partners and several research areas, some on additive material development, also on subtractive and additive manufacturing, software development, but also concerning life cycle analysis and process analysis. So with my colleagues, Michela and Pierre Diaz, we are from ESTIA, Institute of Technology, and we are here in the south of France, in the Basque Country, close to Spain. So if you want to visit us, you are very welcome to do this. In this presentation, I will first present the global robotic cell to explain what we wanted to do in this project. Then I will try to describe the subtractive methods and the tool system design we implemented. Also software architecture to control the tool system, but also to generate path planning, some results we get. And also maybe something for me at least is maybe the most important thing, the next steps, what we could do using this subtractive method. And what we could do is, I think, something like interactive manufacturing. And then I will conclude and present next work we are going to do. So in HINDCON project, the global robotic cell is this one. So we have a big frame, 12 meter per 12 meter. And inside this big square, there is this big cube, there is a cable robot with 8 cables that will move an additive system to print, so to print concrete structure, and that will also hold a subtractive system to do some machining on the printed structure. So it's called all-in-one, but because of the material we are using, concrete, of course, we have to wait a minimum time before being able to do some subtractive action on it. So on this system, when we have finished to print, we can remove the additive system and we can plug the subtractive system and continue to work on. So it's a large scale because it's a large cable robot and we are able to print also large parts in different places. Now I will briefly present the subtractive method and tool system design. So the idea to be able to do some machining on freshly 3D printed concrete parts. So freshly printed means that we need to wait a minimum time of drying before working on it. So it's concrete material, and we had to make many tests to be able to know what could be the perfect drying timetable. Because if you try to do some machining on already fresh concrete, this concrete can become liquid again. And of course, that's not something we want to see. So we made some experience plans, and depending on the way of printing, the quantity of additive inside the concrete, etc., we finally were able to define the ideal time to do some machining, and this perfect time was between 2 hours and 6 hours after printing. Also, what we envisaged to do was, as machining, was engraving, also drilling and polishing. So we have to study the maximum forces we would have to apply with our manipulator, robot manipulator, because we had some constraints. The maximal payload was 300 kilograms for the cable robot, but we had also some problem with flexibility of cables and this type of thing. So we wanted to be sure that we would be able to apply the forces for machining, even in presence of flexibility on the cable robot. So we made some trials also on this point, and we finally conclude that 2-3 kilograms would be the maximum force for machining operation. In fact, polishing, for example, is requiring only 1 kilogram of pressure. So 2-3 kilograms would be the maximum force. And so we also had to define some control system to be able to do the machining without destroying the part, but also without destroying the robot. So we had to use some force sensors to monitor the forces applied during the machining. So for this, we simply used 4 force sensors between 2 discs at the end of the robot. I will show you later how it was made. So with these 4 sensors, we were able to know exactly what force we applied with the robot on the part. And we can interact also, thanks to our application and some component coming from KUKA called RSI, able to apply some correction on the machining trajectory every 4 milliseconds, so that we can be sure that we are not applying too much effort. And we can also use this force monitoring to detect that we finally achieved the perfect machining operation. So it's a classical feedback loop. But one advantage of using this RSI is that you are simply using industrial robot without any modification. So we use it with KUKA. We did it with KUKA robot, but it could be made with any other robots that would be preferred by operators. So concerning the milling strategy, as already mentioned, effector is attached to a KUKA KR10 robot, a small arm manipulator, and this arm manipulator is suspended to the cable robot. For many reasons, and the first of these reasons is that we were working on a prototype and we did not solve all the problems we could have, like vibration, flexibility, etc. So in the first approach, we decided for our machining strategy to move the arm manipulator at a given place we want to work on, then fix the cable robot. The robot is no more moving, it's a static cable robot, and then the arm manipulator is doing its machining operation on a working area. The radius of action is more than 1 meter, so you can work on parts 2 meter per 2 meter per 2 meters. It's not so bad. And the strategy is to define just a basic trajectory, sweeping trajectory, for example, talking about polishing, just a sweeping trajectory, just define what is the theoretical surface, and then apply the force control, and you sweep in front of the wall, you are polishing, and when the force are almost zero, it means that you have reached the surface, and that's okay. So it's really also easy to program the operation because you do not have to think about the advance you are doing when polishing or when removing materials, and just control the forces. If you do not have any forces, it means that you are at the correct surface, to reach the correct surface. Also, in addition to the force control, as mentioned, we are using a cable robot. Here, the ropes are not metallic ones, so there is a lot of flexibility, and we can have many problems of precise localization and also vibration. So if you want to get correct dimensional results, once machining is finished, you need also to have an external localization system that will help you to correct this localization and to know exactly where you printed the part. So to do this, we use OptiTrack system with several cameras that are here in the red circles. And with this OptiTrack system, we were able to record the printing trajectory. So that's just an example. On this example, you can see that we had also some vibration. So the printing trajectory is recorded, and then later, when we want to do the machining, we use this information to be precisely positioned in regard to the part we want to work on, just before starting subtractive operations. So we had this force control plus the OptiTrack, and thanks to these two tools, we were able to do some machining with not so bad result. We will see later. To define the trajectories and the way of machining. So machining is, just to remind you, engraving, but also polishing, drilling, milling. We use a parametric design programming environment based on Rhino, Grasshopper, and HAL Robotic. HAL Robotic is a plugin that is very useful to program trajectory, but also to do some collision avoidance, simulation, etc., etc. So we use this tool in collaboration with HAL Robotics, and it helps us to take into account the milling constraints, so the tool, also axis orientation, the part geometry. So part geometry could be a wall, but it could be also a picture. If you want to engrave a logo, for example, the part geometry is not only a wall, it's also a picture, and you can do some process on the picture before being able to engrave it. So some strategy, milling strategy, engraving strategy, drilling strategy, etc. You can get the toolpath. You can also do some simulation, tune some simulation parameters, and generate the code and KRL program. We are using a KUKA robot. It could be something else if we use, for example, Stobly or other robot. And this program integrated also the input-output with a real-time controller. In other words, with our application doing the force control and also the localization. So all this stuff were developed during the project. And we finally were able to do some polishing. Here, it's not on the cable robot. It was during the trial. It was like a simulation of the vibration you couldn't get on flexibility. It was put on wood pallets. So you can imagine it was moving a lot. But thanks to this force control, we were able to get a very flat surface. I would say perfect one, at least as good as what we could get with hands. We also were able to do some milling. By milling, I mean to be able to get perfectly flat surfaces and also perfect sharp corners. So the idea with this milling system is not to have only basic flat surface just to have nice surface, but thanks to this, if we are able to get some sharp corner and really flat surface, we are able also to do some assembling of parts. And that was the interesting things. So we can build 2 meter per 2 meter parts, and then we can finish also the parts that we want to assemble. So that was the idea of milling. And we also were able to do some engraving. So from a picture, we can extract, here it's just letters, but we will show you on another picture that we were able also to engrave some pictures. So you can extract the information and then you can work directly on the surface. Here, the tool we were using, this one maybe is not the cheapest, simply because we were trying to do some tests on very hard concrete. So this one was dried after 3 or 4 weeks of drying, so it was very, very hard. Here we were using very classical tool. When you work on, of course, we get nice result, but it was classical tool. Here, this milling tool, and the same for this one, the small one. These tools were very cheap tools. So it means that here, when you want to do some polishing, you have to use some diamond tools. We use 2 discs for polishing, and the cost was something like 300 euros for these 2 discs. Here, we are just talking about some euros tools. This one is 10 or 15 euros, and this one is a little bit bigger, so but it's also very cheap. And thanks to this strategy, so to do machining just after printing on relatively fresh concrete, not too much dry, you can do these type of things, and you can get this type of results for just some euros. And you can also, but we will see it later, it's also a nice opportunity because working on the fresh concrete means that you could remove parts that are destroyed and then you could reprint just after that. So these results, you can find some results also. You could find some video of operations that we made. I know that the HINDCON coordinator put a lot of video on YouTube. And as mentioned just earlier, we think that thanks to this subtractive system, we could add something new into the 3D printing world. Usually, when you are printing, when you are doing some additive manufacturing, you can get some defects when printing. One example on this picture is this type of result you could get. So you have the general shape you want to get, but sometimes you need to do some additional work on it because it is not ready to use part. You have something to do.
Joseph, sorry to interrupt you. 2 minutes more.
Okay, in 2 minutes we'll be finished.
Okay,
thank you. So the idea is to add on top of the manufacturing process that is classic. You have your part, you design your part trajectory, you execute the robot command, and then you get the raw mechanical parts. The idea is to get some feedback. This feedback able to do some machining before manufacturing again. There are many tools now coming from augmented reality and tangible tools. For example, here it's just an example where you can make a drawing. From this drawing, you can directly get the CAD information to be able to print and to get your results. Some people also try to do some integration of sensors on tools so that they can build a first thing, then they can get the CAD drawing, they can get trajectory, and then can print it again. What we want to do is something more. Instead of dealing only with geometrical design, we would like to get also some feedback through different type of peripherals, so that we can get some information about the health of the part you are printing. If there is a big default like this one, you can be informed, you can analyze also the results, and then you can print again and define again some new, maybe new geometry or new parameters for printing. So that's the things we are working on now, thanks to our setup. And we think that it's something that people working on 3D printing should think about, to include also subtractive action so that you can do more than just printing, and if you have some problem, you can stop them. So it's my conclusion. We were able to demonstrate that it was possible to do some machining on freshly printed concrete structures. The results we obtain in terms of surface were, we think, promising, because we are more or less able to do some assembling thanks to printing and machining. And we think that many new applications could come from this, because printed parts are not always very perfect. So adding subtractive action could help to get complex shape and parts that could be used. And concerning the future works, well, we made some experience plan to get the perfect drying time, but we think that we could also sensorize the material, so to include inside or from the external, we could try to monitor the situation of drying to optimize the application of machining. And the most important thing for us is the interactive 3D printing with correction of printing defects and redefinition of course of shape during the printing also. And here you can see that we had also the possibility from a picture to do some engravement. So, well, and that's all for me. Thank you.
Thank you, Joseph, for this very interesting presentation. Unfortunately, we have to move to the second presentation because otherwise we will go out of time. So if there will be questions, maybe the attendees can interact later with Joseph, even by using the interaction channel that we have in our Teams. So thanks again, Joseph, and let's move to the second presentation that is given by Diego Montoya-Zapata, generation of 2.5D deposition strategies for LMD-based additive manufacturing. Diego, the stage is yours.
Hello, everybody. Can you hear me?
Yep.
Okay.
Yes.
I will share my screen now. Okay, again, my name is Diego Montoya-Zapata.
Diego, we cannot see your presentation.
Oh, okay, you can't see?
No.
Okay, I will try to do it again.
Thanks.
Can you see it now?
Yes.
Okay, perfect. Thank you. As I said, my name is Diego, and I am here to present you our work on the generation of 2.5D deposition strategies for laser metal deposition additive manufacturing. So first of all, a little bit of an introduction on the on the laser metal deposition process. This is an additive manufacturing process in which powder or wire metal is deposited onto a substrate, a metallic substrate, and this deposited material is indeed melted by a high power laser. This process has several applications on repair, coating, refurbishment, or remanufacturing of high valued industrial pieces. I mean, based on this application, on this wide range of applications, we focus on a particular thing. We wanted to study and to develop the path planning for the laser metal deposition process, in particular for a 2.5 axis machine. So here, let's say a brief survey of the literature. We found, first of all, we found that path planning plays an important role for several reasons. Some of those are, let's say, well known because the path planning determine the time spent and the material use also, but it also plays a role in the structural integrity to avoid some defects such as pores or non-fused powder, and also in the mechanical in the mechanical properties in the microstructure. We've also found, let's say, some research on how to generate different infill strategies or different infill patterns. We can find, let's say, spirals, raster based, and some other based on the medial axis calculation or on the contours and the offset of contours. So let's say there's research on that. But we found few works that tackle the problem of the generation of the intralayer and interlayer transitions. And what we mean by a transition is that, like, the repositioning of the tool head while the laser is not active. I mean, we need to connect 2 points in which we are going to deposit some powder in our case. We need to generate those transitions. Let's say, as I told you before, our ultimate goal was to generate the path planning for laser metal deposition for a 2.5 axis machine. But I haven't told you an additional thing to consider, an additional requirement, is that the material supply is continuous. That is, even when the laser is not active, the material is still being fed to, let's say, to our domain. So it was important to consider this let's say, this issue, because if you come across the build part while the laser is off, then some non-fused material is going to be deposited on top of the substrate. So this kind of thing, this kind of issue could generate some defects on the building part. For example, some pores, maybe some poor adhesion for the next layer, and maybe some poor surface quality. So we had to consider this additional requirement, and so we developed some strategies that effectively avoided the previously deposited layers. So here I want to show you, let's say, the workflow of the generation of our trajectories. We have first, let's say, our domain, our region. In this case, is a 2D region. We first focus on the geometrical things. We wanted to generate the infill of this region. In particular, we implemented let's say, a very simple infill. It is formed by by parallel lines. And once we have generated this infill, then we could, let's say, generate the trajectory. Here a little bit more on the infill generation is like for the infill, we wanted to consider two additional things. The first thing is that our region could have holes, as in this case. We see that this region has some holes here, the white part here and the white part here. And also in the holes may be some additional materials, like some islands of material. So we wanted to consider that. And we also wanted to consider that each of these regions that have to be filled could be filled using, let's say, different infill patterns. So in order to get that, we basically decompose our 2D region into a tree hierarchy. Here we have, let's say, the root polygon right here. And then we have the two holes of this polygon. And additionally, we have here let's say, the island of material inside this hole. And later on, we were able to generate the infill for each of the polygons that have to be filled, considering its holes. After that, we have then to generate the trajectory. So once we have let's say, the infill for each layer, we are able to generate the trajectory for each one of these layers. And finally, we have to generate the trajectory for the full part. That is to generate the connection between the different layers. And so right here, let's say, is the most beautiful, let's say, part of the work. As I told you before, we were dealing with a system that was constantly supplying the material. So we had to generate some trajectories that were able to avoid the previously deposited layers when the laser is not active. So for this strategy, we use some graph-based approach. So this is right now I'm going to try to explain you our approach. So this is the problem we were facing. We had to connect 2 points, P1 and P2, and there is a region right here in blue that we have to avoid. So we can see that if we try to connect P1 and P2 directly, let's say with a straight line segment, we would cross this region. So we wanted to generate a trajectory that was able to avoid it. So here in the image on the center, let's say we have again the same configuration and some additional, let's say, some additional path. So we have here in black is the bounding box of the region with an offset. And we have some, let's say, paths that connects the points P1 and P2 to this black box. So what we need to generate our graph, so is first of all we have P1 and P2, and so we have these nodes 1 and 2 here in the graph that corresponds to these points. Then we have here in red, let's say, the connections between P1 and the box, the bounding box, which is in red here in the graph, and which are in red here in the geometric configuration. And we have also the nodes that connect the P2 to the bounding box. Here, I mean, once we have right here the nodes of the graph and the edges of the graph, there's one more thing that we added to our graph, and is that the edges have a weight. So that, let's say, that weight is basically the distance between the points in the geometric configuration, except for those edges that crosses the region we wanted to avoid. In this case, we set the weight as infinite. So right now we have, let's say, a graph, and we have to connect the nodes 1 and 2 in this graph. So right now we have a graph problem. So what we did then was to find the shortest path in this graph that connected the points 1 and 2. What we did was to implement the Dijkstra's algorithm for this task, and let's say this is a graph problem, so you may implement other algorithms such as A star, for example. So here we can see, let's say, the solution for the problem that we were dealing, I mean, in this example. And here we have let's say, the corresponding geometric path that we generated for these 2 points, or to connect these 2 points. So now some results of our, let's say, of our implementations. Right here we have some infills that we are able to generate. In the first image here we have, let's say, a simple infill, a simple polygon with some vertical lines. Here now we have a little bit more complex polygon which has a hole. And here we have, let's say, even more complex polygon that have some holes and some miles of additional material inside these holes. And finally here we have, let's say, a complex one in which you can see that, let's say, every fill polygon has a different infill pattern. That is, the direction of the lines of the infill lines right here can vary between fill polygons. And here we have another example, let's say, now of the generation of the trajectory. Here we have, let's say, an undesired path. We want to connect this point here in grid to this point red here. So you can see that if we try to connect them like directly, we cross the polygon. So this is the thing that we want to avoid. So in our implementation, we were able to generate this valid path in which we were able to avoid the region and to connect these points in our, let's say, in a valid fashion for our considerations. Here we have some, let's say, some full trajectories that are generated with our software, with our implementation. We can see in the image on the left, let's say, 2 particular things. The first thing is that each layer may have a different, let's say, an infill direction. You can see here that the direction of the lines is changing along each layer. And you can see also that the connections, when the laser is off, that is the blue lines right here, these connections can, let's say, are always away of the polygon. They are always like coming around it. And here we have, in the second image, in the right-hand side, we have an example of a trajectory for, let's say, a more complex region, which have some holes and some materials, and some islands of material inside them. Here, we were able to validate our approach with a real laser metal deposition machine. This is a powder fed one. These are, let's say, two examples of, let's say, here in the left, a simple polygon. This is a simple square, and on the right hand side we have a polygon with a hole. And here, let's say, we use 316L stainless steel for the, let's say, for the physical experiments. And those right here are some parameters of the experiment: the laser speed, laser power, and the powder flow rate. And finally, to summarize a little bit my presentation here, so I've presented here like a methodology for the generation of the path planning for a 2.5D laser metal deposition process. We have, let's say, incorporated a region avoidance algorithm that is based on the graph generations of the problem of graph abstraction of this problem, which somehow alleviate a little bit some hardware limitation that is the continuous material supply. We implemented some, let's say, basic trajectories which are like zigzag data, and we are able to build parts with these trajectories. The trajectories we generate are able to build parts that may contain holes, and we were able to validate these approaches via a powder-fed laser metal deposition system. And so as future work, we know we have a lot of work to do. I mean, first of all, we want to focus on the implementation of other infill strategies, as the ones that I mentioned before, such as spirals, some contour based or others that are based on the generation of the medial axis. We know that we have to focus also in some, let's say, in like the optimization of the trajectory. However, here we have like, there's different kind of things that we can optimize. That is the build time, maybe the material waste, but also some more, let's say, mechanical related things, maybe the mechanical properties, or to avoid the heat concentration in some zones. So this would be an interesting thing to work on. And finally, we want to generalize this path planning for a more complex machines, those that have 5 or more axes. So this is it, and thank you all for your attention.
Thanks a lot, Diego, for this very interesting presentation. If there are questions, please raise your hand. Yes, Joseph?
Yes, I have a question. Yeah. But maybe it's not a perfect question. Maybe I missed some point. I just was wondering if you took into account also the thermal dissipation, the thermal law, when you want to avoid all, when you want to make stop, when you want to start again on another part of the structure. Because it could have some impact also on the constraints that we can get from this part later on when it will be finished. So just to know if you take into account the thermal law, the thermal dissipation.
Okay. Thank you, Joseph, for your question. Let's say actually not right now. We're not considering it, but we know we have to consider it in the future. I mean, we know that. Let's say it. I mean, with the laser, we have I mean, we have a thermal process. We know that 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 this kind of things will have an impact on the final piece, in the mechanical properties, on the life of the build part. So we know we have to consider, but let's say this is for the future right now.
Okay, I'm definitely not a specialist in this field, but some colleagues of me are working on it.
Yeah.
And also are doing this thermal modeling with reduced modeling.
Yeah.
And try to include it in the parameters tunings.
Yeah.
And we are not so far from your institution, because Vicomtech,
Yeah, exactly.
are you? Yes, if you are in San Sebastian,
Yeah,
I think
we're
it
in
could
Basque
be.
Country. Yeah.
Yeah. So it could be interesting to meet.
Okay.
Maybe if you want, we can exchange, and I can give you some contact with my colleague working
Okay.
on
Okay.
it.
That would be very nice. Yeah. Yeah. That would be great.
Thank you.
Okay. Thank you, Joseph.
You're welcome.
Okay. Other questions? There are no additional hands. So we move now to the third presentation of this session. The title of the presentation is Functionalized AM Parts for the Manufacturing of the Future, and the paper will be presented by Michela Sanguedolce.
Thank you for the introduction. And I am now sharing my screen. Good morning, you all. And our paper will be about additively manufactured parts for the manufacturing of the future. In this slide, you can see the outline of the presentation, which will be about a brief introduction about industrial manufacturing paradigms, a comparison between additive manufacturing and conventional manufacturing, and the varnishing process, which we selected for this work. Then we will talk about objectives, materials and methods in terms of experimental procedure and simulations, and the results concerning surface integrity, residual stresses, and high cycle fatigue tests, and then conclusions and future works. As all of you may know, during time, different industrial manufacturing pillars evolved. The first one, the craft production, was related to the first industrial revolution, and then the second, third, and fourth related to the following industrial revolutions. The first one was characterized by a high level of product customization, but at high costs. The following third pillars will growingly involve will improve the enrollment of the customer into the production process. The first one was characterized by a low level of customization, but low costs and high productivity, while the second one take into account an improvement in terms of variety of products, but not still involving the customer into the production process, as the number of designs were still limited. That's why with the fourth industrial revolution, Industry 4.0, and this means a new pillar is today affirming the mass personalization production. And one of the means of Industry 4.0 to boost the last one is additive manufacturing. In fact, if conventional manufacturing is still considered the best choice in terms of costs drop when low complexity goods need to be manufactured, for which regards high complexity goods and highly customized products, additive manufacturing guarantees a significant cost drop. Also, it enables to manufacture a near-net shape product within a single step, while conventional manufacturing often requires the relocation of the semi-finished product from one machine to another. But we need not to forget that additive manufacturing has some drawbacks in terms of reliability of the produced components. In fact, if these components need to be subjected to severe working environment, additional post-processing stages are almost mandatory. In terms of post-processing stages, in this work we will talk about the varnishing process, which consists in a severe plastic deformation and chipless process. This process is performed through a rigid roller or sphere, which is progressively pressed into the surface of the sample, and it smooths the roughness and asperities of the sample itself, thus promoting the removal of microcracks and voids resulting from previous production process, and thus increasing fatigue life, high corrosion resistance, and strength of the component itself. This process can successfully replace other post-processing finishing processes, and also recent developments concern the fact that varnishing can be applied to complex shaped parts, and thus giving a perfect match between additive manufacturing in the framework of Industry 4.0. Going to the objectives of this work, we meant to activate two pillars within the Industry 4.0 framework. The first one, the 3D printing, the second one, the simulation. In fact, through 3D printing and post-processing varnishing, we meant to assess the capability of this process to effectively enhance the quality of the components, thus promoting a flexible process chain. While with the simulation, we meant to validate a model in order to reduce experimental effort and to make it easier to produce a highly customized product, but at an affordable cost. Also, with the combination of the first 2 points, we had the purpose to reduce the environmental impact in terms of waste and auxiliary materials. In fact, the simulation can bring to a significant reduction in experimental effort, and also using environmentally friendly processes such as using environmentally friendly lubricating techniques, these points can be reached. Also, we meant to boost the customer integration into the process according to the concept complexity is free, intending that if more complex parts need to be manufactured, but also the quality of the part needs to be preserved, there should be no significant costs. Also, the introduction of secondary processing operations can enable the enlargement of the research space for the process optimization. This slide, you can see the setup used for the experimental campaign. On the left side, we have the dog bone sample with a rigid varnishing tool, lubricant delivery systems, and a thermal camera, which was used to monitor the temperature during the processing. On the right side, you can see the high cycle fatigue setup test. The material used in this work was GP1 stainless steel in shape of metallic powder, which was processed using a laser powder bed fusion process. The samples, once removed from the sintering substrate, have been stress relieved and machined in order to remove the external layer of the, which results in unmelted powder residuals, thus preparing the surface for the following process, which is roller varnishing. This process was carried out under minimum quantity lubricant conditions. This lubricating technique is a perfect trade-off between the environmental issues, the environmental impact of the use of due to the use of lubricants, and also the surface quality after machining, which in dry processes it results it often results in problems in terms of wear and surface roughness. In order to evaluate the effect of the varnishing process and different conditions, high cycle fatigue tests have been carried out, as you've seen also in the picture of the setup. Concerning the simulation, the model for the process was created through the FTC deform software, and it was modeled in 3 different steps. The first one was slowly pressing a rigid tool into a plastic workpiece in displacement controlled motion. The second one consisted into putting into rotation the workpiece in order to transmit the motion to the roller. And in the third step, the varnishing force was evaluated in order to calibrate the depth of varnishing imposed. As concerns the simulation, the validation of this model can bring to ideally unlimited number of simulated experimental tests, which can correlate the varnishing conditions and industrially relevant variables such as surface and subsurface hardness, roughness, and residual stresses, and thus allowing a significant reduction of costs related to experimental tests and scraps generated in order to produce a customized product. As concerns the results, we have noticed the varnishing process can help to improve surface and subsurface quality of the samples in terms of reduction of the surface roughness up to a 62% with respect to the Asterned sample. Also, in terms of hardness, the surface hardness can be increased up to 117% with respect to Asterned conditions, while with respect to the sprinted ones, up to 163%. Also, we noticed a significant introduction of beneficial compressive residual stresses and a porosity reduction. All these factors mutually interacting favored the improvement of high cycle fatigue of the samples. In fact, as you can see from the picture, with respect to the sprinted samples, we reached up to 100% increase in high cycle fatigue life compared to the only 20% given by the sole turning process. In conclusion, we can say that the design process can flexibly satisfy Industry 4.0 requirements without affecting the final quality of the product required. Also, the support of a reliable simulation model allows us to optimize the analyzed process, significantly reducing costs as scraps generated, and thus reduce the environmental impact and costs related to treating waste, which also the use of environmentally friendly lubricant conditions enables the creation of a safer and healthier working environment. This process chain could be easily applied to companies which already employ systems which are compatible with consistent with the ones mentioned here. And our future works can involve broadening the application of this methodology to other mechanical processes, all the mechanical processes such as shot peening, which already involve the use of primary processing techniques such as additive manufacturing. Thank you for your kind attention.
Thanks a lot for the presentation. Questions? You can raise your hand if you have questions. I do have a very minor question, I would say, because just to understand a little bit better, you mentioned that these new processes can be applied to you have called new generation companies in the final slide. Are you already in touch with some companies or manufacturing system that they would like to apply what you have proposed in this article, or you have already identified the, I don't know, a product or a manufacturing process to make real application?
This is a relatively new approach we are taking, but I think we can successfully find some companies. In fact, aerospace companies are already interested in studying such processes for the engines. But I think there will be further development in these terms.
Okay, thank you.
Thank you.
Hi, Michela. I have a question, Michela.
Hi.
Hi, this is Satish here. So I have a question regarding the additive manufactured part. So which process was used for the part that you tested? Was it like laser sintering or some like powder welding, or I'm just trying to understand.
The laser sintering was the process. We used an EOS machine. The powder was deposited and progressively melted through a laser beam.
Nice.
Layer by layer.
And about the functional design part, I don't know if I missed it in the part of the presentation, but what was the intention of the design? Was it designed for reduction in weight or just reduction in processing time, or trying to understand the functionalized part?
As you already may know, 3D printed products are really affected by the internal quality given by the additive manufacturing process in terms of high porosity and high defects and cracks which are generated, and also the surface quality is not adequate to the high cycle fatigue working environments. So the functionalization was intended as an improvement in terms of surface and subsurface quality in order to increase the fatigue life.
Okay,
I don't know if I answered you properly.
No, thank you. I understand that. Thank you. Yeah.
Thank you.
Okay. If there are no additional questions, we can move to the last presentation that is given by Marta Rinaldi. The title of the article is The Impact of Additive Manufacturing on Supply Chain Design, a Simulation Study. Marta.
Hi, Francesco.
Ciao.
Hi, everyone. Can you see my presentation?
Yes, perfectly.
Okay. Hi, everyone. I'm Marta from Italy, and today I'm going to talk with you the impact of additive manufacturing on supply chains. Okay, first I will briefly introduce the literature and the scope of the work. Then I will present the steps of my research, later the numerical results, and finally some limitations, conclusions, and future developments. Okay, additive manufacturing is a manufacturing technology which is completely different from the subtractive manufacturing solutions. And in the last decades, many researchers have started its impact and its performance compared to traditional manufacturing. Many studies focused on its growing potential, but also on some problems linked to the massive production. In the last years, the impact of additive manufacturing on supply chain performance has started to be investigated, and some authors have discussed interesting effects. For example, this technology allows to reduce the number of components and raw materials, having positive effects on inventory management. And additive manufacturing also needs strong collaboration with suppliers, and this partnership increase the service in terms of quality of raw material and on-time delivery. And moreover, it promotes home fabrication, and it involves the customer in the design step, and creating dynamic connections with customers and offering the possibility to give quick response to the market. And finally, its flexibility and the promotion of foam fabrication have a positive effect also on the supply chain lead time. And despite the impact of this technology on supply chain performance has been discussed in literature, the impact of the technology on the supply chain design and reconfiguration received less attention. But this technology implicates a new manufacturing concept which strongly influence the structure of the supply chain and also the relationships between the players of the supply chain. As said, it promotes home fabrication and in general a decentralized production strategy, and it also reducing raw material and components drastically reduces the number of suppliers. For these reasons, additive manufacturing is considered a potential disruptive technology for supply chains because it completely revise or even create new configurations. And nonetheless, very few studies have measured this disruptive effect on supply chains. And for this reason, the aim of this research is to evaluate and measure the impact, the effect of additive manufacturing on supply chain performance, focusing on the supply chain structure and considering different configurations. So different configurations have been modeled and tested in order to understand the performance of the supply chain. And in particular, both traditional and additive manufacturing have been studied and modeled in order to understand their performance and compare them. And in particular, one configuration based on traditional manufacturing has been modeled and compared with two different configurations based on additive manufacturing. A discrete event simulation model has been developed in order to test the behavior of the players in considering different configurations, and a set of key performance indicators have been defined in order to measure the supply chain performance. The aircraft spare parts industry has been chosen for this study, and supply chain structures modeled and studied have been defined starting from a case study from the literature. And as said, 3 different configurations has been studied and modeled. And the first one is based on traditional manufacturing strategy. And in this case, we have conventional centralized supply chain with just one producer who manages and controls the world production. And he supplies the product to 2 big regional distribution centers who serve smaller warehouses located close to the final customer. The second configuration is based on additive manufacturing, but it maintains a centralized structure. And the idea is to model a supply chain similar to the previous one and just changing the production strategy. And in this case, the 2 regional distribution centers become both producers, and they serve the smaller local distribution centers located close to the final user. Finally, the third configuration is based on additive manufacturing too, but it consider high decentralized structure. And in this case, the production phase is split and located close to the final user. And in this case, each local distribution center is equipped and he is able to manage its proper production. Okay, concerning the simulation model, as said, discrete event simulation model has been developed and 1 year has been simulated. Different service level have been tested in order to understand the feasibility of the solution, varying the quality of the service provided. And overall, we test 33 different scenarios. And since the customer demand has been modeled as normal distribution, 25 replications for each configuration have been launched. Logistic data in terms of lead time and travel distance between the players were obtained by the literature. And here you can see the other input data of the model. Concerning the logics of the simulation model, each player has been modeled considering its role in the supply chain. And in particular, distribution centers, both local and regional, manages the product distribution and sale. And so its inventory management has been modeled in the simulation model. And a proper inventory policy has been defined, considering periodic reviews and a variable order quantity. And moreover, the safety stocks vary and depend on the service level. On the contrary, the manufacturer manages the production phase. And in this case, we inserted in the model a sort of production flexibility. In fact, a production nominal quantity has been defined considering the expected demand, but during the simulation, the producers can slightly increase or decrease such quantity. And in order to implement this logic, a double check has been implemented. And in particular, first, a monthly check is performed, and a monthly production quantity is defined considering the demand of the previous month. But each day, the manufacturing checks the current inventory position and he defines the final quantity to produce. Here you can see the 6 key performance indicators defined to evaluate the performance of the supply chain. The first 2 indicators allow to evaluate the performance of the production phase. And we have the capacity utilization, which reflects the machine saturation. And if more than 1 producers exist in the supply chain, an average value is calculated. The second indicator is the number of machines, and which depends on the productivity of the machine. And in this case, a total amount of is calculated, considering all the producers of the supply chain. The other 4 indicators allow to measure the performance of the whole supply chain. And we have the customer satisfaction, which depends on the stock out amount, considering just the players who face the final user. The supply chain lead time, which reflects the time needed by the supply chain to transform raw material into final product. Sorry. Finally, the total holding cost, which reflects the cost of storing both raw material and final product, and the total transport cost, which reflects the cost of moving both raw material and final product. Okay, now some results. And in this case, I will show an average value considering the 25 applications launched for each configuration. And the first graph shows the supply chain lead time trend varying the service level. And in this case, we can see that in general, additive manufacturing provides a better solution compared to traditional manufacturing. And in particular, the decentralized structure provides the best solution, and it also shows high flexibility. In fact, in this case, the supply chain lead time is not affected by the service level. And this is due to the fact that increasing the service level, the stock level and the related time in stock just grows slowly. And for the same reason, the total holding cost shows a similar trend. And in this case, we can see also that the centralized configuration in general, both additive and traditional manufacturing, need a higher stock level and thus higher total holding cost. The total transport cost shows a different trend. In fact, in this case, this indicator is not affected by the service level. This is due to the fact that increasing the service level, the average amount of stock increase, but the number of and kind of deliveries remain the same, and because the demand doesn't change. And the different values between the three configurations depend on the structure of the supply chain and the number of echelons of the supply chain. Okay, then we have the customer satisfaction. In this case, we can see that all the configurations provide good results, and this is probably due to the logics implemented in the simulation model, and in particular to the flexibility of the production phase, and also on the the proper inventory policy implemented in the model. Anyway, also in this case, the additive manufacturing provide the better solutions compared to traditional manufacturing. The last two indicators show an opposite trend. In fact, in this case, traditional manufacturing can exploit its centralized production with a higher capacity utilization and a lower number of machines. And in particular, we can see that additive manufacturing has a number of machines which is considerable higher than the traditional manufacturing solution. Okay, as a conclusion, just some general conclusions, and we can say the use of additive manufacturing allows designing a shorter supply chain and providing benefits in the supply chain performance. And we can also confirm that the combination of additive manufacturing and decentralization provides the best solution in terms of supply chain performance and the high flexibility. On the other hand, the machine productivity still limits the economic feasibility of this technology. As a limitation, we can say that these studies is mainly focused on supply chain performance, but in order to test the global suitability of the solution, both production and the supply chain costs should be computed. And as a future researchers, we could solve this limitation, and we also could conduct a sensitive analysis in order to test different input data and measure the reaction of the supply chain. And in particular, we could vary the customer demand and study the related supply chain performance. And another future development, we could also implement in the simulation model a multiple production strategy. That's all. Thank you for your attention.
Thank you, Marta, for your presentation. If you have questions, please raise your hand. In the meantime, I have just a question. Did you carry out verification and validation for your simulation model? You know, the simulation model should be able to recreate in some way the real supply chain that you are considering. So did you carry out some verification and validation?
Well, in this case, it is difficult to validate the model because we didn't reproduce a real supply chain, but I mean, anyway, we have validated the model because the results of the simulation model are in line with the results of the provided by the literature. So
you carry out validation by using literature?
Yes, in this sense, we have validated the simulation model. Good,
very nice.
Thank you.
You're welcome. If there are no additional questions, this was the last presentation. So thanks a lot for attending the presentation. We do have now the lunch break. Sessions will start again at 2 p.m. Central European Time. Thanks a lot.